So today is going to be a lecture that starts out with, as you've seen maybe, a couple of papers, 2 or 3 I think it is. And these papers represent sort of the transition between casting and MIM. And as such, they cover a lot of basic issues. They talk about comparisons between MIM and standard cast processed alloys as well. And they cover a lot of things that we've talked about in class in terms of furnace atmosphere and compaction and particle characteristics and all sorts of issues that are directly pertinent to everything we've been discussing so far. So I think it's important to go through these, which is why, as I said earlier, I killed a bunch of trees so that you could have something that you could work with. And also, of course, this is very similar to what you might see in a test, an abstract-based question on a test. And so it's important that you be able to go through these and read and understand and relate to concepts that we've talked about in class. And so that's why I'm going to the trouble of going through this. But partly, so this is about 20 years old. This stuff, the end of the 90s basically, and we're making the transition. So you see a lot of things that are familiar, but don't get the impression that they don't worry about this stuff anymore. They still worry about it, the same things. But this is kind of saying, okay, now that we're gradually moving from old style to new style, here are the things we need to concern ourselves with. And you'll see a lot of familiar themes in terms of what we cover and what we talk about. And then, if I give myself time, then we'll make a transition to micro MIM at the last third or so of this class. All right, and so starting here, and what we're talking about is net shaping of cobalt chromium moly. So F75, that alloy grade that you should be familiar with, which is kind of the standard cobalt chrome. And this guy is looking at net shaping. Let me find the right. There it is. Net shaping of cobalt chrome via metal injection molding. And so that's a very basic title, and that represents the fact that he was one of the first people to publish it in this area. Looking at MIM, and whoops, he's got a lot of things here that are relevant to what we discussed. And so we're looking at near net. No, that is not what I wanted. Near net shaped complex parts for medical, automotive, industrial, and consumer industries. And so that kind of covers the gamut of things that we've talked about so far in class. He's looking at cost reduction of orthopedic implant devices. All right, and so cost reduction refers to the fact that it's net shape. You don't need to machine it. All that expensive machining stuff is minimized or hopefully eliminated entirely. And he's looking at process parameters of liquid phase sintering behavior of injection molded ASTM F75. And so this is a liquid phase that involves the formation of a transient liquid alloy. So this is phase diagram magic, basically. And you have these temporary molten components that show up and then get absorbed back into it. And so he's doing things that we've talked about. You mold them, you debind them, you sinter them using different atmospheres. All right, so all very familiar to us now. And then critical at this point in history is comparing to the cast and cast/hip ASTM F75. So he's trying to say, is this stuff as good or better than what's out there in terms of casting? So this is a historical question. And then he's talking about the liquid phase MIM F75 greater than 500 and 900 MPa with an elongation of 17%, thus exceeding the minimum requirements of ASTM cast F75. So what he's saying is that with MIM, we can make parts that are better than the standard technology, which is kind of the gold standard. You don't want to be able to do stuff that's the same. It's got to be better in order for people to adopt it. So if you ever get into the startup world, especially, that's the rule. And so he's looking at tensile strengths of 500 to 1,000 MPa, elongation of 40%. And then he's talking about density. We'll go through that in a second. He also talks about fatigue resistance, which for these biomedical alloys, we walk on them millions of times during their lifetime, so that's why he's interested in fatigue resistance. And then various other things as well. So moving on, assuming I can, there it goes. All right, so he's talking about the fact that metal injection molding, so net shape manufacturing, I should say manufacturing route, for complex parts. Very complex parts at volumes ranging from 10,000 to 1,000,000 parts per year. Precision of plus or minus 0.3%, which is certainly better than what you would expect from casting. Cost savings from 20-50%. And so it's just everything we've discussed. Feedstock preparation, molding, debinding, and sintering. All right. And then he talks about fine metal powders, 20 microns in size, which isn't all that fine. And then everything that we've discussed, all this stuff should be familiar to you at this point. So you should be able to read and understand a lot of what we're talking about. Linear shrinkage, 12 to 25%. So all this should be just, obvious to you at this point, reading through this. And so this is where you should feel pretty comfortable. And at this point in history, the two most commonly used MIM materials were medical applications 316L, which we've talked about, and 17-4 pH stainless steel. So some stainless steels that are used in medicine. All right, nothing fancy about that. Workhorse materials for nearly all medical MIM applications. And so he's talking about making forceps, jaws, surgical blades, orthodontic brackets, and staplers. And so these are the this is the workhorse stuff. This is the not sexy but important things that we use to get medicine done inside the human body. And keep doing that. And so he's talking about a surgical blade. So what he means is you want to make a knife, and you want to make a knife by injection molding. All right. And so this allows you to do that and have that sharp edge, so sharp in fact that it doesn't require much machining to sharpen. All right, so this gives you an idea of not much mass in a knife, but how sharp that edge is. Orthopedic surgeons care a lot about sharp knives. All right, but this allows you to make things in such a way that it's near net shape and only needs a little bit of work to get to being a useful knife. Rather than starting with a big block and cutting into thin sections, you just injection mold these things and you have the thin sections right out of the furnace. And then other things like femoral components we talk about a lot. Tibial trays, that's the lower part of the total knee. Cable crimps, boring stuff like that again, surgeons, they go through that like candy when they're doing operations. And then he's also talking about wax-based MIM processes. So we've talked about wax-based MIM process and thicknesses less than 6 millimeters. Okay, and so he's talking about the fact that you need to get the wax out, and the thicker it gets, the more challenging that can be. And this relates to the fact that you can have gradients in carbon, so the surface may be more deprived of carbon than the interior, all right, which isn't always a bad thing. It depends on how you use it, but it recognizes that there are some limits to how deep you can go and get all the wax out. So that's what he's referring to here. And then he's talking about the fact that we have water-based and water-soluble binder systems of slight improvements over the wax-based polymer system in terms of their ability to debind relatively thick cross-sections, okay? As far as I know, again, this is reflecting, this is reflecting the, can you grab that for him? I'm tired. Thanks. This is reflecting the fact that they tried water for a long time. The guys over at Battelle, over there across the street, they tried to do injection molding with water-based systems, and as far as I know, the wax-based high-temperature systems are kind of won out. I'm not aware of any water-based work that's going on. But he does talk about catalytic debinding, trying to get things out, designing the polymers to make the process of polymers unzipping and falling apart into gas-based molecules that can be removed. That's all part of this catalytic debinding. And then making thicker parts, which have important uses. But again, you have to think about eliminating the need for support fixtures during debinding. All right, so this is the furniture I talk about repeatedly. So you have to try to get these things out of the furnace in one piece, and ideally that piece has the right shape. And so that's what he's referring to when he talks about fixtures. Okay, any questions about this so far? Starting particle size, chemistry, and sintering atmospheres. Something? Hold on. Yeah, I did. Objectives in the MIM process, high sinter density. Okay, that should be familiar to you guys. Exceeding 95% of the theoretical. For ceramics, we know it's even more demanding, but for metals, they're forgiving, so 95% is pretty good. And he's talking about tissue ingrowth here. That was the coating idea when back then they were still looking at putting beads onto the surface of a cobalt chrome implant and sintering them onto the surface to give bone something to grow into, which we talked about. And starting particle size and sintering temperatures are different for the two applications, very different. Let's see. And then, very importantly here, minor variations in levels of carbon can lead to significantly different sintering response and hence affect the density and mechanical properties. All right. From a sintering standpoint, process control is much easier for a material containing little or no carbon versus one requiring carbon within a tight tolerance. All right. So this, speaks to the idea that we know we need carbon, we know we need certain amounts of carbon, and we don't want to get it too far away from the amount that we're targeting. All right, so that's what he's referring to here. But again, carbon is required to impart strength in F75, so we cannot eliminate it. Things go south if we eliminate it. So we leave it in there. Unlike CIM, where you got to get it all out, here you have a certain control over the amount that's there. And then this is a reflection on where things stood at the time. No published studies, results of the static and dynamic of F75 via the MAM process. That's changed a lot, all right? There's a whole bunch of studies now, but he was the first in this particular area. So we want, as it says, a fine microstructure, properties intermediate between cast and wrought, F75. And let's see. Hit conditions, microstructure parameters, grain size, and then something we really haven't talked about, but biocompatibility is not ingest and study. That was true at that time. Of course, they've beaten the heck out of biocompatibility since then. All right, very important in terms of how the surface of a cast part may have different chemistries than an injection molded part, and how the body responds to it. Turns out doesn't respond all that differently. But anyway, he was acknowledging the fact that they hadn't looked at it back then. And then again, he's comparing it to cast F75. So he's trying to make it at least as good as, if not better than, casting. All right. Again, reflecting where things were when this was published. Any questions so far? So again, as I keep saying, this is something that you guys should be familiar with. You should be able to read through and more or less understand a lot of what's in this. And we got this nasty chemistry. All right, typical of a lot of these alloys, where you have cobalt and chrome, yes, moly, yes, and then a whole bunch of little stuff, all of which is designed to bump the transformation temperatures up and down. And then, so this is just governing, telling us what there is they're making. We go into a picture of this. Did I miss? And that's shown here in this image. So it is what you expect it to be. And actually, again, we're talking about doing this in the lab, setting up a lab to do this, where you have the injection molded one, and then you have the sintered one. And the injection molded one looks exactly like the sintered one, except the sintered one is smaller because you've removed the binder, which made it shrink, and then you've sintered it, which also made it shrink. All right, but this is the goal. So it comes out of the mold looking exactly like what you want it to be. Now, these guys are just doing some 4-point band and tensile testing, but if we're making a part that goes into a human, this is also the goal. All right, injection molded, sintered, full density, right properties, right shape, without very little machining. Of course, again, as I keep saying, femoral heads are bright, shiny, smooth, so obviously we have to machine for that, but at least you don't have to grind away a block to make a sphere. All right, so that's your motivation right there. And then they talk about looking at sintering temperature, time, and atmosphere were optimized based on the microstructure. Okay, so there is no computer program you can go to and say, tell me what atmosphere I should use. You just have trial and error, gut your way through it, figure out what the properties are at the end of it, and that's going to vary as a function of sizes. And they're looking at 1340 to 1380 C, pretty darn high in terms of temperature. And then reducing neutral and a proprietary atmosphere. So right away, this is the interesting thing, so right away, just in the transition, they're already talking about proprietary atmospheres. They're saying, I'm not going to tell you what it is I use because it works well for me and I want to make money off of it. So I'm not going to tell you exactly what it was. But they're going to say we have reducing, which we know means hydrogen, neutral, which we know does not have hydrogen or oxygen in it. It's probably just argon or argon nitrogen. And then something they come up with that works really well. That is some blend of nitrogen, argon, and hydrogen. Okay? Any questions so far? So you're following along, right? These should all be familiar themes I'm hitting on. So we've talked about this extensively, and now you're seeing it put into practice. See, solution annealing, followed by water quenching. This is something they do in metallurgy. They drop things out of a furnace into water. That's nice if you can do it. temperature range from 1200 to 1250. Ductility improvements due to dissolution of grain boundary carbides. Okay, so right away we're talking about what happens to what's at the grain boundary and how, as it sits at high temperature, those carbides can diffuse away through the lattice. All right, and that is the dissolution process, based on diffusion, not based on melting, but diffusion of these things away from the source in the microstructure. All right, and you should be able to read through this, and like I said, it should all be, I mean, some parts of it are not going to be familiar, but in terms of what we've been talking about in class and a lot of this. All right, and so this is not familiar because we haven't really talked about this, so I don't want to get into issues of phase diagram, but there's a supersolid sintering response in the range of 1350 to 1380. So during supersolid sintering, a partial melting of the pre-alloy powder occurs above its solidus temperature to form a liquid phase, which provides for rapid densification via capillary forces and particle fragmentation. So the second half of this should be familiar to you. The first half is phase diagrams. All right, so you form these transient liquid phases in the phase diagram. If you want to go look at that, you can see it. And that liquid phase sits at a certain temperature. And the beauty of it is it does its job. It has capillary forces that pull things together. All right, and then as you cool off, it goes back to being a solid. It goes back to being the alloy you're looking for. All right, so this is a nice, clever thing you can do with metallurgy that we can't do with ceramics. All right, and then as I said before, we have these different atmospheres. And the reducing atmosphere, which of course is going to be a hydrogen-containing one, 7.65 to 7.75. And then we're using, as I talked about before, we're using hardness as a stand-in for mechanical testing because hardness is easy. All right, so we have 7.6, 7.75. We go to a neutral. All right, the density goes up, and our properties also tend to increase. But then the proprietary system gives us even better values of density and better values of mechanical properties as well. All right, and so this kind of relates to that, what was it, 2FE NI system I talked about last time. Same type of measurements and some of the similar types of processes. You find something that works for you, gives you the best properties, best density, everything's a plus. But you can be sure that they didn't just say, okay, we'll use this. They spent probably a year coming up with the data that says one atmosphere is better than another, easily. Any questions about that? All right. Relatively insensitive changes in the sintered density between 7 point and blah, blah, blah. And as it says here, sample sintered in a reducing atmosphere exhibited a much lower hardness between hardness values 8 to 12 and lower sintered density. All right. And so you have a lower hardness because why? In the reducing atmosphere, you're pulling out what? The second one, carbon. All right, you already got, the oxygen came out earlier. Now you're pulling out the carbon. All right, so he's saying that you don't want to do too much of this reduction. You do want to remove the oxides, but you don't want to take the carbon out. At least you don't want to take too much of the carbon out. All right, again, should be familiar to you in terms of what we're looking at here. You should be able to rationalize these types of behaviors. We know that that hipping gives us a better densification, and therefore we get better properties. So that all should be pretty straightforward. You should be able to see echoes. And the use of reducing and neutral atmospheres lead to relatively low strength. And let's see, best mechanical properties are retained using a proprietary sintering atmosphere. So we know what it is, we're not going to tell you, resulting in an outstanding combination of ultimate strength and ductility. And then, as before, solution annealing, which we know can be necessary, results in the elimination of grain boundary carbides while preserving the sintered porosity. So you get to the porosity you want, and then you start removing grain boundary carbides if you sit there at a high enough temperature for long enough. And so consequently, the ductility and ultimate strength improved over the as-sintered alloy as expected. And then hipping gives you solution annealing, but gets rid of porosity and the carbides, but results in grain growth, all right, which isn't necessarily a good thing. Again, the system likes to grow its grains. We don't want it to. It's not paying any attention to what we want, and the grains will grow anyway. Corresponding decrease in the yield strength but a significant increase in the tensile strength, reduction in area, and ductility. All right, and this is nice. This is advertising here. Superior ductility of metal injection molded F75s compared to its cast counterpart. So this is what you want, better than the state of the art, and they can say that. And there's comparison of different properties showing that the MAM stuff is better. And so, yeah, we think about hardness as being important, and certainly it is. Ultimate tensile strength certainly important. Elongation, the nice thing about that, what is that saying is that the metal injection molded has fewer flaws or smaller flaws. That's what that is really saying. That elongation is better than what we get, so it means it's less flaw sensitive. All right, and so there's a bunch of things here talking about how this is important, and they also, this is a many years long study of what they were doing here. Fatigue endurance limit 428 megapascals using smooth geometry, which compares favorably with F7. It means they went and they did some testing at millions of cycles. All right, that's how they came up with that number. That didn't happen overnight. That took a long time. Dimensional control biocalculation have not been reported yet, but it turns out they're not that significantly different. Okay, so as he says, first published study of static and dynamic F75 processed using MIM. Okay. So again, you guys should be familiar enough that this all seems pretty straightforward. You should be able to read through this and have some passing familiarity with a lot of what's being said. It's about that. Does it seem fair that you could understand this? So I can take a paragraph from here, pop it on the test, and you'll say, oh yeah, I know that, right? I'm saying you'll see questions like this on the test. Now whether it comes from here or not remains to be determined. I think if you look at some of the old exams, which I'll post, you'll see passages from this on those old exams. But it might be from a different paper entirely. All right. Okay, and then this is another study which is a little bit of a tangent, but it does talk about things that we've been discussing. The possibility of producing biocompatible, porous, functionally graded metal acetabular cups using powder metallurgy techniques where a porous surface provides a substrate for incorporating a polymer compliant layer which is supported by a rigid inner core. What is that translating? He says that we want to make a cobalt chrome moly cup, all right, and inside of it we want to put a polyethylene liner that then penetrates into that metal metallic acetabular cup. All right, so they want to have pores in there so that the polyethylene will go into those pores and form a really strong bond. All right. So I'd love to tell you this is what's done now, but it's not. But the point being that this is a real problem even now. So in the Iowa study we had going on, it was a very common problem that the polyethylene liner would get loose and rattle around. All right. And then when that rattled around, that means that the head could also rattle around and come out of the cup entirely because the polyethylene was rattling around. So it was very annoying. And when the titanium bumps up against titanium, they both suck at wear. So that was a problem when it happened. Okay, or else the cobalt chrome would bang into the titanium, and you put titanium onto the cobalt chrome because titanium is terrible when it comes to wear. All right, so anyway, this sounds like a silly thing that should have been solved but has not been solved. But anyway, so they had this idea of making these gradients in pores and getting the polyethylene to go into those pores, which is a tall order because the polyethylene is like 1 million molecular weight, incredibly high viscosity. So you need incredibly high pressures to get the polyethylene to go into those pores. And no one is doing this today. All right, so you can't, they don't do this in biomedicine. But it was a noble effort, let's put it that way. And so it's important to us because we're talking about water atomized powder and a novel bimodal powder. As it says, each had a different powder morphology, leading to differences in compressibility, which shouldn't surprise you, and sintering behavior, which also shouldn't surprise you. Okay? Compaction pressure, sintering temperature were used to produce porous materials containing 5 to 33% total porosity, so they're playing around with the porosity. What is the right number to get the polymer to flow into these pores? And then again, there are also, as before, different atmospheres, vacuum, argon, and a flowing mixture of 75-25 hydrogen to nitrogen, which is a pretty high hydrogen content. And then, as always, you have to look at tests of hardness, tensile strength, and ductility. What did we make? How good is it? What are its properties? Is it suitable for this application in the body? And then variations in surface chromium. Okay, so we talked about aluminum being volatile. Turns out chromium itself can also be volatile under these circumstances. Nitrogen and carbon content, which you should now know is extremely important in terms of controlling the properties of these materials. And as they verify differences in properties, although the lower the bulk porosity, the better the properties exhibited. Yes, sir?
What would be the difference if you, let's say, raised like a high nitrogen content and a low carbon content versus vice versa?
What if you what?
If your atmosphere, let's say you were to raise the nitrogen content and leave the carbon content low, what would be the difference?
Well, the atmosphere is nitrogen and hydrogen, and the carbon content is what comes out of the alloy. I'm confused. I'm confused.
Okay, so then nitrogen and hydrogen.
Yeah. Yeah, so we know that hydrogen extracts carbon, right? And the higher the hydrogen content, the more carbon extraction this system will undergo. So if we raise the nitrogen and decrease the hydrogen, then we have less carbon extraction as a result. We need some, we absolutely need some to get rid of the oxide. The question is, how much do we need beyond getting rid of the oxide, and what does it do to the carbon content?
Okay.
Does that make sense?
Yeah.
Okay. All right, and so he talks about these issues here. You know, it's all very important, but not part of the process. Let's do this and skip the second page. No, it is no second page. Oh wait, let me go back. Okay, so they talk about the idea of incorporating a polymeric component layer to the bearing surface of a fully dense acetabular cup to give rise to this cool idea: fluid film between the cup and the head through elasto-hydrodynamic lubrication. All right, this was kind of a wish list at the time, where if you have one surface and another surface and you have a layer of water molecules between them, and those two surfaces never touch, but they float on the water in between those two ideas. And that was the concept here, which didn't pan out because we can't make surfaces that good. But that was the general thought here, is that you glide on the water. So anyway, but they were looking at this, and the problems they were having is that the polymeric fully dense cup using 4 fixing locations, but this cup only lasts a few weeks testing on a hip joint symbol. So they were using standard technologies to fix the polyethylene cup to polyethylene liner to the metallic cup, but it would come loose in the simulator, which is a bad thing. And it also comes loose in the humans, which is also a bad thing. So they wanted to have hundreds of surface pores, suitable locations into which the polymeric compliant layer could be bonded. And so again, that was the general motivation, but didn't ultimately work out, but they made a good shot at it. So cobalt chrome moly, gas atomized, or a different way, prep processed, and they're looking at fully dense surgical implants, but neither the powders themselves nor the consolidation processes can be easily altered to produce porous parts. All right, and so they were looking at water atoms, cobalt chrome, as one possibility. Low oxygen contents, compacted, blah, blah, blah. So there are people playing around with this. They're also interested in looking at femoral stems with varying porosity from a dense metal core to an outer open polymer network. Why would they want this in the femoral stem? So this is the other side of the implant. Why do they want those pores there? Bone growth. You want bone growth on both surfaces, right? Both the top and the bottom of the implant, you want bone growth. And let's see. We talked about this before. Porous material could be impregnated with lubricating fluids or plastics. Not that that's significant here. And yeah, so let's go ahead and skip all this. Go over here. Metallic porosity graded acetabular cup into which a polymeric component can be incorporated to replace the current cup available. So again, ultra high molecular weight, very high porosity. If they wanted to go to a lower molecular weight polyethylene, then there's issues there. But anyway, they were trying this out. And they have water atomized cobalt chrome. Okay, so we should know that water atomized cobalt chrome is not as nice as the gas atomized stuff. And then, let's see. high proportion of large spherical shaped particles. 3 powder size fractions were used in subsequent sintering trials, mechanical tests. So they sieved them. So they produced different particle sizes. We know this is partly looking at the 1/7 rule. We also know that these 3 different particle sizes can have very different effects on the sintering properties. And so relatively large pore sizes. Each fraction was vacuum annealed at 900 C for 2 hours to soften the powder and to reduce any oxides present. All right, so you know you're pulling out carbon, and you're also getting rid of oxides in these particular materials. And we don't need to go the rest of that. That's just the details. And so the chemical compositions involved here. And they looked at cold compacted at pressures between 470. Whoops. Anyway, come on. Do what I want. All right, there we go. Between 470 1235 megapascals. I looked this up. This is like 100,000 psi. All right, downstairs we do like 3,000 psi. So this is way, way, way higher pressures than you guys may have ever seen. Manual uniaxial press with carbide die inserts because everything is still bloody hard. They didn't use any lubricant, and then they, as compacted, looked at sintering and different types of atmospheres, different types of techniques, and then they took a look at the porosity as a result. And let's see, and talk about making the darn things, so forth and so on. Mechanical testing, Vickers hardness. Again, it's always easier to use a hardness test to get properties than tensile tests. And they did do ultimate tensile strength and yield strength and so forth. So from there, we talk about morphology. So this is showing you things that are roughly spherical. What? And sphericity was linked to powder size. Smallest particles more rounded than these particles. So looking at these guys, they have the water atomized guys on the left, and then the milled stuff on the right. So neither one of these looks as nice as what we saw with the spray atomized powders. They're kind of rounded, but they're nowhere the beautiful marbles we get from spray atomization. We don't have that here. But they still can use it, all right? And then on the right-hand side, they have the milled stuff, which is really ugly because they broke apart what they had from the other process. All right, and then they have statements here about the fact that, and this should be familiar to you, both water atomized and ball milled powders proved it's extremely difficult to press, resulting in low green densities at comparatively high compaction pressures. So even though they're applying 100,000 psi, they can't overcome the fact that the force chains are not efficient at transmitting pressure. All right, they squeeze the crap out of it, but they still can't get these things to densify very well. And pore flow properties from the ball milled powders, not a surprise. Ugly powders, not very good force transmission. All right. Prettier powders, better force transmission, at least better than that. And pore compaction characteristics exhibited by this powder, they didn't get mechanical interlocking. And crumbled upon ejection from the die. That's how bad it is, all right? They had pretty good pressures on the outside, but the inside was just loose powder. So you took it out of the die and it just fell apart. Even at 100,000 psi. It's just huge pressures. Still not enough to overcome these barriers. And so they have differences in green density as a function of compaction pressure, which should surprise no one. And then they have powder particle size and compaction pressure. So they had obviously coarse fraction, high porosity, low compaction pressures, fine fraction, water atomized at low porosity, compacted at high pressures. As compaction pressure increased, higher green densities led to higher cinder densities. That should be a duh statement. Of course it's going to do that, right? You reduce the diffusion distances, you get higher densities. And let's see. So the rest of this should be reasonable. And I talk about cinder density and so forth. So I could, easily take one of these graphs, throw it on the test, and say, explain this graph. That's the kind of thing you should be thinking of in looking through these papers. And then we have issues of atmosphere. Atmosphere. Water atomized cobalt chrome moly powders, considerable sensitivity to sintering atmosphere, especially for the fine powder. Fraction sintered in argon. Neither sintering under vacuum nor sintering in the 75-25 significantly altered the final center densities. More open pore geometry may have enhanced the movement of the atmosphere through the sample and assisted in reducing the surface oxides and the powder particles. And so the compaction and how efficient that is controlled the ability of the atmosphere to go into this during the sintering process. And so this is a finer detail that we need to think about in terms of how we design that porosity. All right. Marked difference. Come on. Marked difference in final center densities, which indicated that sintering under vacuum produced the lowest center densities, whilst obviously they're British. If you use whilst in the paper, you're British. Flowing molecular mixture of 75% hydrogen exhibited the highest center densities. All right, and so we get the highest center densities with the hydrogen. Let's see. And then they have microstructure. So we talked about just densification, which ignores everything else. But then we look at microstructure as well. And the oxygen content was reduced in all cases, not a huge surprise, as was iron in the water atomized sample, iron, nickel, and silicon in the bimodal powder sample. So we're pulling out stuff. We're changing the composition of this by these exposures, by these sintering atmospheric exposures. Not only is carbon at risk, but we have other components of these alloys as well. While sintering in a flowing molecular mixture increased in nitrogen content in both powders, should make sense. Nitrogen can go into these things. We know it can modify the transition temperature, so nitrogen becomes part of the structure. Higher nitrogen content water atomized powders is probably linked to more open pore geometry. Again, geometry is being used to control chemistry. The pore geometry has influences on that. All right. So getting back to this. Under vacuum, small carbides were seen sited at grain boundaries. The amount of size of these carbides decreased as the sintering temperature increased. Should make sense. More diffusion, higher temperatures, things go away from their sites. More carbides were seen in the water atomized powder compared to the bimodal. Revealed EDX significant chromium loss occurred up to the first 20 microns of the compact due to the dissociation of oxides, such as CrO2, present on the outer surface. So what happens is you get chromium oxide. It's volatile at these temperatures, and you lose chromium. Again, so it's not just a heat it and get what you started with. All right, and then argon, significant differences in microstructure of the two powders. Coarse powder samples, small grain size with high volumetric quantity of discrete carbides sited around the grain boundaries. And it's different from what happened under vacuum. It should make sense because chromium volatilization is not going to happen as easily. Neither is decarburization under these argon sintering conditions. And here they talk about the fact that you have these different eutectics that can form. We're not going to go into that. But obviously, the amount of these carbides left behind can control the properties. And then, as it says here, sintering under flowing molecular mixtures significantly alter the microstructures again. All right. All right, so hopefully that's pretty clear. These are also some SEMs showing you these are all the same scale bar, but we have very, very different grain sizes. Really large here and relatively small here. Carbides on the grain boundaries in some cases, not always, but in some cases they're sitting where they should be. And you can just look through this and get an idea of the struggles they went through to get these things to give them the properties they were looking for. Okay, so let's see. Let me make sure I at least summarize this for you. Similar porosity values, the individual particle fractions. Okay, so variations in initial powder morphology change the packing characteristics and therefore change the diffusion of the sintering atmosphere throughout the compact. All right, so how that atmosphere gets to the rest, the bulk, is determined by the pores that are present following the densification process. And then that also reduced the formation, size, and type of the precipitate formed. Sintering atmosphere had varying effects. Vacuum can cause things to go away. Argon can be more protective, giving you more carbides. If you use the 75-25 hydrogen nitrogen mixture, you can get nitrides along with also the carbides. And then you get very different properties as a result. Those should make sense to you. And we can look at these porous materials with both high and low total porosity. And again, they don't actually go to the trouble of trying to get polyethylene to go into these things. But what I expect from you when you look at these statements, all right, these should be kind of familiar. Like I said, you should be able to read through this and say, yeah, I kind of more or less understand that. And this is what he said, a couple of lectures ago. Does that make sense? Okay. All right. That was the general goal there. All right, any questions about that? Or what? So then we'll move on to the newer stuff. And this is micropowder injection molding. And this reflects the push in medicine towards smaller and smaller components. It reflects the push towards combining components together to make simpler components that can be used in various forms of medicine. And the fact that we're trying to squeeze everything down so it works with the biological scales that are involved in the human body. And I'm always reminded of, there's a cheesy movie in the 1960s called Fantastic Voyage or Fantastic Journey. I forget which one it is. And it involves this, they put people in a submarine, and then they shrunk the submarine and they injected it into the brain of the general, and they were supposed to drive their submarine around inside the guy's brain, or get to the brain and get rid of some clots in his brain or something like that with this laser mounted on the outside of the submarine. Very cheesy, very dramatic. They were attacked by white blood cells, and it was high drama because they were attacked by white blood cells. Anyway, but that always reminds me of that. We have tiny, tiny stuff doing discrete things inside the body that are very, very important, okay? And it would be nice to have that submarine for a lot of different things. But anyway, this is moving in that direction. So we're looking at things that are very small. So standard stuff like tubing and valves, these guys are, if you open up a little packet of sutures, you'll find these inside of it, and they injection mold these things. And these are surgical knives. They don't look like knives, but they're knives. They have sharp edges. The surgeons use these to cut the sutures when they're done putting them in place. And these are made by straight up injection molding with a little to no machining necessary at the end of it. So it's nice. And then this is a part, and that's a ballpoint pen tip. All right, so things are getting very small. These guys, little plastic parts. Anybody know what these are? Whoops, come back. Might be familiar to you if you've seen enough biology. I don't know. That's a match head, obviously. So they're pretty darn tiny. What's that?
I feel like I've seen them before, but I can't remember.
Yeah, you probably have. So this is, if you've got the inner ear and the eardrum, on the other side of the eardrum is the stirrup, and it looks exactly like that. So that the wide part of the stirrup is on the inside of the eardrum. And so as you have vibrations, it's transmitted from the eardrum to the stirrup and then into the neurotransmission that tells you how loud sounds are. All right, and so obviously what we're doing here is we're replacing something that was lost either due to a congenital birth defect or some type of injury so that people can hear again, because you can go ahead and put this on inside of an eardrum. It heals in place and allows them to hear. And the issue here is that all of this is really small, okay? And so these dimensions obviously are pretty tiny, and if you take that stirrup and cut it in half, you'll see you got maybe 100 microns tops from one edge of this to the other. And so that means that everything we were talking about becomes even more important, because if you have a 100 micron span in that tiny part, you can't have a 100 micron grain, all right? That's a disaster. That's a huge weak link in that structure. So you've got to shrink everything down so that when you cut across this microstructure, you see many, many small grains, which drives everything toward the nanoscale, obviously, okay? So that's kind of why we're talking about this, because everything we've been discussing becomes even more important when I talk about this micro powder injection molding. So there's a global trend towards medical miniaturization. Not making submarines yet. The people talk about that, but they never have done it. Not only of individual components, but of entire systems. All right, trying to make things as small as possible. And in doing so, the manufacturing use of micropowder injection molding, so it's got its own name now, is considered one of the most important manufacturing techniques. You get an optimum combination of economic benefits. Low cost, because you don't have to machine the darn things to these tiny, tiny shapes with tiny, tiny dimensions that are very important. Multifunctionality, new markets. Ecological factors include small dimensions, low weights, low material, less energy consumption. Now they've got this global growth rate of 20% per year is predicted. I don't know if that's actually being hit or not. I see that a lot. But anyway, it has reached a relatively mature state for the manufacture of a variety of microstructural components from polymers, metals, and ceramics. And then in the context of medicine, this is particularly significant because we talk about biopharmaceutical manufacturers requiring new micromolded components to create tiny, less invasive, and or space-saving micro devices. And you talk about pharmaceuticals, you can use these things to deliver drugs. That's what that's referring to. All right, so not only do they have mechanical functions, not only can the tissue integrate with tissues, but they can also deliver drugs to those tissues as well. And so the familiar target here, the inner ear, a lot of experimental things go into the inner ear first. And you can make this biocompatible titanium stirrup, and it'll integrate just fine with the bone around it. All right, the bone still likes titanium, and so this is good stuff. Make exact copies of whatever you have, so you can go to Acetabular, take that out, duplicate it, and then injection mold those parts using very fine powders. And it was limited stainless steels, but you can use titanium now, which has much better compatibility to the bone. And so we think about this due to their need to fit into tiny and delicate arteries, all right? Pumps, catheters, endoscopes. There's a lot of work on making endoscopes that were originally made from 10 parts into just 2 parts. There's lots of reasons for doing that. Challenging geometries, and so you want to cost reduce this so that they do not have to be assembled under a microscope, all right? When everything's really tiny, it's kind of hard to put together. You don't want to have someone tinkering trying to get these 2 tiny pieces to fit to each other. It's just injection mold the whole thing so that it's one parts. And one example of this are powder inhalers, which were once more than 20 parts, are now fewer than 5, so that's an advantage. And then this idea of drugs being compounded or added to them, so they may have gears and levers and so forth and drive mechanisms, but they also deliver drugs at the same time. All right, and so that's a pretty high. The good news here is that the forces involved are relatively small. You can tolerate the pores that might have the drugs in them. All right, so that's how that works. And they are directly implanted in the body, at least for short periods of time, if not longer than that. And so these are some examples of things that you can see. That's again the inevitable match head comparison, but you can see all those parts are relatively small. They can fit into each other, and we have to think about how to assemble that, or else we make it all as one piece. And this is an example of a drug delivering component, and so that's a 100 micron bar. All right, so everything you're seeing here is well under 100 microns in size. And so you've got these posts, and not only do those posts have a certain geometry, they have these little dots, raised pillars on top of them, and then next to those, which is probably the reason for these, you have these pores, and drugs can diffuse through these pores while this is acting as a gear, the overall structure, for example. Everyone see that? You can get fancy with these things. So for these micro parts, slightly different characteristics. Scale issues, finer powders must be used. A decrease in particle size results in a higher viscosity, which should make sense. All right, we should be able to explain why the viscosity is higher. For good moldability, you end up needing a lower solids content, which is unfortunate, but it is the way it is because of the fact that you're working with very small dimensions, and so friction at the walls and so forth becomes higher, so it's harder to go to higher solids constraints. You get high relative shrinkages and sintering tolerances. You must use fine powders to get to the high surface qualities and the small details that we just saw a minute ago. These also exhibit high sintering activity, which is good because it can allow lower sintering temperatures in the context of some of these things, and higher strength in the end. So that's a handy combination of things. Differences from MIM. Diameters here, and talking about ceramics, less than half a micron for ceramics. That's just a standard. Again, think about the fact that you're bridging a distance of 100 microns, and so you want to have lots of grains. So you start out with very small particles so that in the end you have lots of grains. About a micron for pure metals, or maybe less than 5 microns for alloys. It's typical in these cases when you start doing this for these metals, you're not working out in the open air. You have a cabinet and everything is under argon. All right. And so that's how you justify all this. Replication of details down to a few microns with sufficient quality. Moldability decreases at higher fluid densities with a narrow particle size distributions. You'd want to have broad or multimodal size distributions to decrease the viscosity, okay? So we should know the answer why. So we're again using this furnace rule to try to jam more particles into a smaller space, all right, and give you these lower viscosities as a result. On the other hand, Nick, broad particle size distributions cause extensive grain growth. All right, so you mix large and small particles together, and you heat it up. So large particles are going to gobble up their tiny neighbors. All right, which isn't always a good thing. All right, so you end up with a giant grain in between those two 100 micron spaces. You've got a problem in terms of mechanical properties. So, packing density increase by multimodal. High packing densities, the particle shape should be spherical. All right, we know we can do that. We know that gas atomization gives us those. Rounded, or at least equiaxial. Why? We don't want plates. All right, plates flow like crap, or we don't want whiskers because those don't flow very well either. We want nice rounded things with nice rounded things next to them that are smaller than them, so we get everything to be homogeneous in terms of its flow. So, the issue of short shots we talked about, that's important for big parts. It's very important for these tiny parts, where the restrictions can be even more severe. We do know that spherical parts reduce the strength of the compacts after debinding. We should know why, because they don't stick to each other very well, all right? The saving grace is that these are very small parts, so the effects of gravity tend to be minimized, so it's not as bad of a problem, but it still is an issue. If you have irregular particles, the handling is simpler as the strength of the green compact is higher because they interlock with each other. We've talked about that. So that's, again, you're playing the game. When you have these smaller particle sizes, agglomeration is an even bigger problem than it was before. All right. So because of their high surface area, they show an increased tendency to agglomerate. Why is that? Because the particles are small, meaning that surface forces and their ability to act on these tiny particles is larger. You have a big particle, surface forces aren't so much as important, but tiny particles, those guys can get very close together and get stuck into that energy well. Agglomerates can cause cracks in the injection molded state, or the brown, as it's called here, after debinding compact. In a sintered part, strength limiting defects can occur. We should know why. We usually try to destroy them by grinding and or during the feedstock compounding processes via shearing. We know that shearing is necessary, even more important here than it was for the larger particle sizes. And then, of course, we have to use processing aids. So stearic acid comes to the rescue again, all right, because that stearic acid can get in between, form the hairy layers, use entropic repulsion to keep those particles from falling back into the energy well. Make sense? Sound familiar? Yes? Okay. So, this whole area is just everything else that we talked about scaled down. Resulting powder particles should be distributed homogeneously in the organic matrix. They should all be coated with binder so that they don't fall back into that energy well. And any agglomerates that are formed should ideally be soft and not hard. We don't like the hard ones. We can live with soft agglomerates in this context in many cases. Even with very intensive mixing. So we shear the heck out of it, and then time passes. And they come into contact with each other, and they start building agglomerates as time passes. We can't shear it as it's being injection molded, all right? We have to stop at some point and shoot the darn thing. But ideally, that doesn't have big effects on properties. The beauty of it is, this is all very familiar in terms of what we're using. Similar to what we used before, thermoplastic, giving green strength, lots of familiar names here. Often are combined with waxes. You should know why. What is the role of wax? How does it help the process? How does it control the microstructure? You can have at least 3, often up to 5 different organic components, so you can make these things very complicated. Reduced viscosity, all right. Better debinding behavior. We should know why for both of those behaviors. And then we end up with a stepwise debinding process to avoid high pressure or stress in the green compacts during debinding. Now, it's not as bad as bigger parts because the dimensions are smaller. It's easier for gases to get out, but we still have to worry about it. And then, this should be no surprise, processing aids become even more critical because things are smaller, surface sources are more important, and so we need to have all those surfactants and dispersants involved. Binders are hydrocarbons and therefore are nonpolar hydrophobic. Contrast, the ceramic powders are hydrophilic, so we would otherwise get poor interactions. However, we use surfactants such as nonpolar hydrocarbon chains like stearic acid, having the functional group, so again stearic acids, various other things. The interaction with the polar sites of the powder results in a powder surface with hydrocarbon molecules so that it will blend with the surrounding polymer phase around it. And then you get better mixing with the non-polar thermoplastic and or wax-based binder components. All right. Any questions so far? So this should all be kind of a review, but it's in a different direction, and we should have a reasonable idea of why we're going in that direction.
It'd be easy if I knew what was going on the first time around.
The lectures are there online. You can listen to them as much as you want. All right.
Help me.
Okay, and I've graded 4 out of 6 questions. I was shooting to have it done today, but I couldn't get enough time yesterday. So I will have them done on Wednesday.
How look so far?
Yeah.
How are we looking?
Let's say the standard deviation is probably going to be a little large. I don't know. We'll see how it turns out in the end. Some good, some bad. Anything else?
Mine is gone.
I'm sure yours is 100%. I'll see you guys on Wednesday.
Still hunger fighting.
And just ignore this page.